So this time we'll talk about efficiency tricks for neural nets. And I'm going to start by talking about the glamorous life of an AI scientist. So a few years ago, there was this ad in, I believe it was Paris, or somewhere in the French-speaking world, on this, cologne ad, and this says a artificial intelligence researcher. So obviously, this is a very in-demand occupation nowadays.
Is it an ad for YSL?
What?
Is it an ad for UCL?
Yeah, it is for this cologne. This is a real ad, and this is a real AI researcher. So obviously, he's setting the bar very high for all of us in various ways. But in reality, this is probably more like what your daily life looks like, as opposed to being in cologne ads. So, so you could spend more time posing for cologne ads and less time looking at your TensorBoard logs. I'd like to explain a little bit about why neural networks are slow and what can we do about it. So there's a lot of things that we can be doing. And one of the biggest things is to use specialized hardware like GPUs to train your neural networks. I think a lot of people might have started to think about this. If you haven't started to think about this, on AWS you can get GPU machines, and that would be something good to do. However, GPUs love big operations, but they hate doing lots of operations. They're very fast at doing big operations, but slow when you ask them to do lots of things. So we want to reduce the number of operations through optimized implementations or batching. Another problem is networks are big and data sets can be big. So even with good batching, running them can be slow. So there are ways to use parallelism to process many data at once. And finally, in some cases, even with parallelism, even with GPUs, if you're trying to do things that are just too computationally expensive to be tractable, then you run into problems. So we can do approximate operations, so approximate operations. So I'm going to talk about GPU training tricks first. This is maybe the biggest. Win that you can get immediately. And to give an idea about training on GPUs, I have this very simple and maybe overly exaggerated conceptual difference between GPUs and CPUs. So a CPU, I feel, is kind of like a motorcycle. Or maybe if I wanted to put it in an even better way, maybe it's like a really, really fast human runner. So they can accelerate to top speed very, very quickly. And are versatile, can do lots of different things. On the other hand, GPUs are more like an airplane or a jetliner, which is that CPUs are quick to start and their top speed is not too bad. On the other hand, an airplane, it takes an hour to get boarding. It takes another 30 minutes on the runway, but once you start flying, then you're really, really fast. So that's kind of the conceptual difference between the two. Another reason why I kind of mentioned maybe it's more like a really fast human sprinter is also CPUs are very versatile and can do lots of things that GPUs can't easily do. So that's another difference here as well. So I calculated a simple example. This was with older hardware from a couple years ago. But this is a matrix multiply. Where the matrix size is anywhere between 16 and 2048. And note that these seconds are in log scale. So this is like, this is a microsecond, and this is a second. So a 16 by 16 multiplication here on the CPU takes a little bit more than a microsecond, maybe 2 to 3 microseconds. On the other hand, on the GPU, it takes 15 microseconds or something like that. Then the 32 by 32 matrix multiplication takes, sorry, that's actually more like 50 maybe. So 50 microseconds. A 64 by 64 multiplication takes 50 microseconds. So you see the GPU, despite the fact that you're making these bigger, it doesn't get slower at all. It just eats up the operations. And if you look at the relative accuracy increase, also in log scale, over between CPU and GPU, you can see that the CPU is 20 times faster when you're doing a single 16 by 16 matrix multiply. They're about the same when you do a 128 by 128. And once you start getting up to 2048, you can see the GPU that I had at the time is about 30 times faster than running it on a CPU. And the reason why is because the GPU, the way they work, they're massively multi-threaded. So they have 256 or 512 threads that are all running at once, whereas a CPU has a single thread that's running at once. Of course, you can do multi-threaded CPU computation as well, but CPUs are not built for efficient multi-threaded computation like GPUs are. So basically, they don't see anywhere near the kind of like almost linear gains that a GPU sees in doing this multi-threaded computation. Yeah.
Shouldn't that ratio be GPU over CPU? It's 30 times faster. GPU.
Yeah, sorry, it should be, this is backwards, you're right. Any other questions? So the reason why this takes time is basically your CPU is dispatching an instruction to the GPU. It might be moving memory to the GPU in some cases. I think I'm not including memory movement time in this graph here, in various other things. So basically, getting a GPU operation started, getting the result takes a significant amount of time. But if it's a really big operation, the GPU does it almost instantaneously. Not instantaneously, but very, very fast. So practically, very often I will use a CPU for prototyping or like running unit tests on a very small network. So you create a really small network of like 4 by 4 matrix multiplies, and you run everything through it to make sure you don't get any stat errors. Maybe you even initialize the weights and have some sort of gradient-based checking to make sure things are working properly. For some applications, CPU can be just as fast or faster than GPUs. So like, for example, if you can't do mini batching because you're doing something that's of a complicated structure that isn't conducive to mini batching, a CPU will very often be just about as fast. But you will see big gains on GPU where you have very big networks or do mini batching or optimize things properly. So at some point, if you're going to run over a reasonably sized data set, you're going to want to use GPUs. Oh, another thing though is, let's say you want to do a large parameter search and you profile your GPU code and you see your GPU code is 6 times larger, 6 times faster than your CPU code. But you can get a 64-core CPU machine for the same price you can get a 1 GPU machine. That means you can still do, 10 times more experiments running on CPUs than you can on GPUs. So the reason why I'm mentioning this is I want people to not be of the mindset that you need a GPU for everything you're doing, when in fact CPUs, especially modern CPUs, are pretty reasonable alternatives. Okay. So now, assuming that we're doing GPUs, just because CPUs you don't have to think about this quite as much. Speed trick number 1. This is just kind of maybe in a way programming common sense, not related to neural networks, but it's a surprisingly common mistake. So something that you can do once at the beginning of the sentence or like one time in the code, don't do it for every word. So why is this bad? Any ideas? Yes?
It's making a copy of files every time and then adding onto it, and hence it's taking more time.
It's making a copy of
the variable values because it's appending.
Maybe that part of Python is relatively well optimized, so that's not a huge problem. Yeah.
Doing a multiplication every time, you could do W times C above this.
Right, exactly. So you're doing the multiplication of W times C every single for loop call when you could do something like this. So this looks a little bit silly, or yeah. Sorry, go ahead.
I was just gonna say, and does Python, does it not optimize for that?
Does Python optimize for this? Not by default.
Okay.
And it especially won't do it by default, for example, if you're calling a separate function multiple times.
Okay.
A very common example of this is using attention in the decoder of an encoder-decoder model. So we're going to talk about this later. We're going to talk about attention and encoder-decoder models later, but there are places in attention calculation functions where basically you will have something that looks like this every time, but you can actually avoid this if you don't, if you're a little bit clever about restructuring your code. And this can lead to huge, not huge, but this can lead to significant gains. So this is something to be aware of. Another thing is reducing the number of total operations. And this is somewhat neural network specific or somewhat like parallel operation specific. So can you combine multiple matrix vector multiplies into a single matrix matrix multiply? So one example would be something like this. So how can we fix this? Any ideas? Yeah.
Concatenate first and then multiply.
Yeah, exactly. So concatenate first. So you concatenate the columns for each of the words in the sentence, and then you do a single matrix multiply, which will give you the same result. So this is another example of something that you can do. This is something that if you haven't widely programmed neural networks, especially for NLP tasks before, you'll have to get very, very used to. This is something that's useful. Things like Dynet's automatic batching will kind of do stuff like this for you, but it won't do it perfectly every time, and not everybody will be using that. So you should be aware that this is something that's very helpful. Yeah, and actually, I'll give an example of something interesting here, where this kind of thing here, reducing the number of operations, can be hard if you're doing more complicated things. Like let's say you're doing a tree or a graph operation or something like that. So what you would normally do here is you would have to do some like clever coding in order to make sure that you're not writing a whole bunch of for loops in Python. So like if you've taken algorithms for NLP and you have written the CKY algorithm that was full of for loops, for example. So if you're familiar with this. So this is not something you want to be writing on your own. Fortunately, there are very smart people who have done this kind of stuff for you to some extent. So, for example, Sasha Rush at Cornell has this thing called PyTorch struct that has implemented things like the CKY algorithm and things like graph operations in this kind of way where you can use it in a single GPU operation instead of multiple GPU operations. If I have time at the end, I'll go into like an actual example of this for the CKY algorithm, but I'll skip it for now in case I run out of time. So like this is just something to be very aware of and not forget later in the class when you're implementing your big models and want them to go fast so you don't run out of AWS credits. So this is important. Finally, reducing CPU, GPU memory data movement. This can be a little bit difficult if you're not thinking about things carefully, because sometimes this is sort of abstracted away in neural network toolkits, for example. But basically, one of the really big bottlenecks is moving memory from CPU to GPU. And so while you're moving this memory, the GPU is waiting and not doing any work at all. When you do move memory, it's nice to do it as early as possible. So for example, if you did for X in words and sentence, input the data for X and then do processing, this would not be as efficient as doing something like inputting the data for all of the sentence and then stepping one by one and doing processing. And the reason why is because while this data is loading, it can start computing in an asynchronous fashion, and this can be efficient. So in some cases, there are even data loaders that basically start loading data for one batch while you're processing the previous batch, so you don't have to wait every single time. So yeah.
What's the difference between data and words in sentence? What is data?
Data would be something like pre-trained word embeddings or something like that. So, or like if you're doing speech processing, it would be the speech signal, for example. So if you're just looking up integer IDs, like you have all your word embeddings on the GPU already, and you're just looking up integer IDs on the GPU, that's actually not a very slow operation, so it doesn't take much time. It's more relevant when you're doing something like loading images or speech or pre-trained word embeddings or something like that that take up have a lot of like capacity, and that takes a long time to move. That's a good question though. Any other questions? Okay, so I have an example of this, which might be a fun exercise for people where this is like all kind of elementary. Oh, actually, it's here. So it's in this efficiency thing. So if you're using PyTorch, oh, that's actually not the example, sorry. So I only have the example in Dynet here, but I have this slow impl.py thing. And if you want to look at this, I've made all the mistakes you could possibly make while writing this code. So it would be a good thing to take a look at this and see if you can identify any of the places where I made mistakes here and think about what you would do to fix it. So, okay. So going back to the PDF. So what about memory? Many GPUs only have up to 12 gigabytes of memory. So memory is a major issue. I say up to 12 gigabytes. Some recent ones like 2080s have 11. V100s, which are the really nice, expensive ones that you have to sell your house to purchase, have 16 gigabytes. And if it's 32 gigabytes, you better have a nice house. So basically memory becomes a major issue. So you can minimize unnecessary operations, especially ones over big pieces of data. So one thing you can do is you can go in and take a look. And for example, if you're multiplying things and then adding a vector, there might be a specialized operation for this kind of linear transform that's implemented in your neural network toolkit. So you don't need to be multiplying and adding. You can do like multiply and add in a single operation, or things like this. Another thing you can do, I'm going to talk about this in a second, is use multiple GPUs. I already talked about this a little bit last class because I got not last class, but a few classes ago because I got a question. But another thing you can do is one of the reasons why you start running out of memory is because your mini batches are too large. So you have a mini batch of 32 examples and that cannot fit on the GPU. One thing you can do is you can, even if you're only using a single GPU, is you can reduce your mini batch size to 16 or 8 or something like that. And then just update less frequently. So update the parameters less frequently. So instead of doing like 4 mini batch backprop mini batch update, you can instead do like 4 1 to 4 update, sorry, backprop with mini batch like do I out of 4. So like you take 1/4 of the mini batch and run your backprop on each 1/4 at a time. So the reason why you would want to do this is because mini batches, or doing mini batching has two functions. One function is to make things faster. So with respect to making things faster, this won't be any faster than, for example, having a mini batch of 1/4 the size. But mini batches also make training more stable in many cases. So like, for example, if you're training a model like BERT or a big transformer model, very often you need to have very large mini batches in order for training to be stable. And if that's the case, if that very large mini batch doesn't fit on your GPU, you can do something like this instead, and that will give you the stability benefits, but without overflowing your GPU memory. So this is an important thing to technique to do.
When you say backprop with
Yeah.
for the mini batch, does it mean that you're combining the loss and like backprop training in all at once, or that is computed, or does it mean that you're doing it?
So that's a good question. So basically, it means calculating the loss and then running backprop using your neural network library. So
backprop would be in the normal mini batch source, like we initially are at a size of say 5. So
right, exactly.
So now we backprop for every 5 there.
And basically what happens is you backprop with the first quarter, you backprop with the second quarter, third quarter, fourth quarter, and each time you're accumulating the gradients for your neural network library. So by the time you get to the end, if you're doing mini batches, we assume each element in the mini batch is independent, which means our gradients are all independent, which means the gradients of the mini batch are equivalent to the sum of the gradients of each of the elements. So by accumulating them here, the sum becomes equivalent, so it's the same as just doing it all at once. Mathematically, anyway, not speed-wise, yeah.
So if you want to backprop like multiple mini batches together, what do you have to save them all in memory?
You do not. And the reason why you don't have to save them all in memory is because you calculate the forward pass, then you calculate the backward pass. And when you calculate the backward pass, the gradients accumulate in whatever place in memory you have for accumulating gradients. And you always need to accumulate gradients in memory because that's how the optimizers work. The optimizers look at the gradients and then do a parameter update. So you do mini batch 1, you accumulate the gradients in the optimizer, in the memory location of the optimizer. You do mini batch 2, and you add to those already accumulated gradients, essentially. But you throw away the whole rest of the computation graph every time, assuming you're using a dynamic network like PyTorch or Dynet or something, or TensorFlow Egress. Because of that, the memory usage, peak memory usage is less. Any other? Yeah.
This is kind of a stupid question, but what is the thing that takes up most of the memory for each element?
That's a very good question, actually. So what is the thing that takes up the most memory? The answer is different for depending on the model you're using. For something like for very large models, some of the time parameters can take up the most. Parameters and also like the locations in the memory for the gradients and the like if you're using Atom has 2 additional things. It has the variance, the rolling average of the variance, and the rolling average of the updates, the parameters themselves. So that means you need 4 times the size of the gradients somewhere in memory, right? So that can actually take up a lot of memory on your GPU. In other cases, if your model's not quite as large, either the hidden states of the model, or if you're doing like a language generation task, like machine translation or something like that, very often the softmaxes over each thing in the output can take memory. So the easiest way to answer this for your particular model is to use a memory profiler. And most neural network toolkits have some sort of memory profiler that you can use to take a look. That's a very good question. Any other questions? Yeah.
So this trick would help with the second thing that you mentioned, right? Like if the softmax was taking most of the memory.
So this would help with anything but the parameters. So this will not help with the parameters or the memory used by the optimizer, but it will help with anything that's computed, including the softmax or the hidden states that you compute for each example. Yeah. Any other questions? Yeah.
Much more on the composition. So there's
Right. Yeah, so that's a good point. I actually hadn't seriously thought about that before, but like if you're using batch normalization, which is a technique that basically normalizes the values to be within a certain range for the entire batch, then this would have an effect on that, and it might make things less stable. Perhaps the reason why I didn't think about this very much is it's actually not super common to use batch normalization for most NLP tasks, and people instead use stuff like layer normalization, which gives you about the same effect, but is independent across the batches. So I think practically for many state-of-the-art models that wouldn't be a problem, but if it is a model using batch normalization, then you might have trouble. Good point. Any other things? Okay. So yeah, I have the example. So now I'm going to talk a little bit about parallelism and how we can exploit parallelism. So there's 3 types of parallelism that I want to talk about here, and this is on a finer, coarser and coarser grain level. So the first one is within operation parallelism. The second one is operation-wise parallelism. And the third one is example-wise parallelism. And the first 2 can be classified into something that's called model parallelism. So model parallelism is basically parallelism that you can exploit even if you have a mini batch size of 1, basically, even if you're not processing multiple data instances at the same time. Whereas example-wise parallelism is something called data parallelism, and this is where you are parallelizing the processing of multiple instances. So within operation parallelism, basically what this looks like is if you have a really big operation, like a weight matrix times a hidden state, you have one thread doing the first part of this operation, second thread doing the second part of this operation, third doing third, fourth doing fourth. So this is precisely the reason why GPUs are wonderful, right? They do this really, really effectively, and instead of having 4 threads, they're actually doing 256 threads, or 512 threads, or something like that. So GPUs and also TPUs, if you're lucky enough to have access to TPUs, excel at stuff like this. There are also implementations for this on CPU. There's one example is something called MKL, which is the Intel Math Kernel Library, and basically this can do multi-threading within matrix multiplies or other things like this. The gains are less striking, and they're so much less striking to the extent where you might actually want to turn off MKL and it will make things faster. So if you're using 32 threads within MKL, you'll probably get like a 2-fold gain. And if you're using 2 or 3 threads, you'll get a 2.5-fold gain. And the reason why is just CPUs are not structured to have really fast like dispatching between threads and in memory, in memory maintenance and stuff like this. And this will hurt caching and all the other kinds of things that make CPUs fast. Interestingly, if you're running neural net training on CPUs, you might realize that if you run 4 independent threads, it'll be faster, but then you start running 8 and you start seeing you don't see linear increases. The reason why is if you think about your computer architecture class and think about like caching and all this stuff that you forgot from your undergrad or whatever, it actually has a big effect on kinds of things like this. So like you're losing, your memory is swapping out of the cache, and that's making it slower to compute. So really this parallelism helps a lot when you're doing on GPUs and TPUs. So next is operation-wise parallelism, and this is the least common variety of parallelism to use, I think. I think most people could get through this class without even thinking about this, and you would be fine. So basically what this is this is splitting each operation into a different thread or perhaps different GPU device. And so if you have a whole bunch of operations that are kind of in different parts of your computation graph and none of them depend on each other, you can split this one into thread 1, split this one into thread 2, thread 3, thread 4, and do all of them kind of in parallel, and then merge the results together for doing something else. The difficulty here is how do you minimize dependencies and memory movement? And basically the answer is this is really only easy to do if you have really big parts of operations that are worth parallelizing. So one example of this would be, let's say you have so one example of this that was done in the original Google machine translation paper is they parallelized the first 2 layers of the encoder on one GPU. Then they had the second 2 layers of the encoder on a second GPU, third 2 layers of the encoder on a third GPU. And all of these, you start computing the first layer on the first GPU, but then once the first time step of the first layers are done, you move that to the second GPU and you start processing. So you have this kind of like diagonal flow of information between the layers and between the GPUs and stuff like this. Does this sound like fun to anyone to implement? Not really, right? So this is why this is not very widely used. Something that might actually be feasible is like, let's say you had 2 languages and you wanted to encode them independently. Maybe you could put one language on one GPU and another language on another GPU and run them all through BERT or whatever you wanted to encode them with. So this is something that theoretically you can do, but it's not really widely done except in maybe very intensive production settings, etc. So example-wise parallelism. This is kind of like this is something that you might be interested in doing for a project, especially if you have access to like a 4 GPU machine that doesn't cost you lots of money to run. So one example would be to process each training example in a different thread or machine. So we have 4 examples like this, and basically we dispatch all of these to different threads or machines and process them independently. So the difficulty here is how do we implement this, accumulate gradients, keep parameters fresh across machines? Fortunately, most modern neural network libraries implement this for you. And they have simple ways you can do this. One example is in PyTorch, there's something called distributed data parallel. And basically the way it works, this DDP here is an abbreviation for distributed data parallel. And you call this around your model, and this automatically distributes the model to different devices. And then when you call this DDP model, it will basically do this distributed processing for you, dispatching the data to the different devices, calculating separately on the different devices, and then merging them together in the end. Yeah.
So when it does this, is it going to be synchronous about the computations of all the devices? So kind of whichever your slowest device is, that's going to be as fast as it can go?
Mm-hmm. So that's a good question. So is it going to be synchronous or asynchronous? I'm 98% certain that this is synchronous. Can somebody confirm this for me? I know some people in this room have used this before. Now the question is, did anybody actually understand what they were doing when they used this? Is this synchronous? I'm pretty sure it is. Yeah. I don't see anybody volunteering information, so that's your homework. You get to go check whether whether this is synchronous or look it up on your computer now. But basically, synchronous and asynchronous. The difference between these are how the communication works, and basically the way the communication works in the case of synchronous processing is you dispatch all of the computations, you dispatch all of the computation graphs to different devices, and then you do the computation, you accumulate all the gradients, and you accumulate them on maybe one machine, and then you do an optimizer step, or you send them out to all of the machines. You do an optimizer step to update them, so now all of the machines have an identical view of the parameters, and then you start the next computation. So the problem with this is, what if you have one machine that's just way slower than the others? Maybe it's overloaded because your lab mate is not being very courteous. Yeah, sorry.
Can't we just distribute the work, like the job that it had with any machine that
Sorry.
Like in that case, we can just give the work, say we had an example, this is an example given thread, like the machine and it is slow. So just give it to machine 3, get the value, like this drop the task.
Oh yeah, so what you could do is, like, if one machine is slacking off or it crashed or something, you could send it out to another machine. But that amount of time waiting for, you know, just like figuring out that it's moving really slow and then dispatching it to another machine.
I believe we can say that this would be similar to map reduce, where we take a lot of something that
Yeah, so let me finish 1 second, and I can talk about MapReduce and connections to that as well. But basically, this is, so if you're doing synchronous stuff, let's just assume that you're not doing anything tricky, and like the slowest machine is your bottleneck. So you have one machine where, you know, your lab mate has used all the memory on the machine and it's swapping and it's moving really slowly or something like that. Or you have a slower GPU on one of your machines. So basically, every single time when you do the synchronous, when you're synchronizing, like let's say this is synchronizing here, you're waiting for that slow machine and wasting the effort that you could be using on the other machines. There are ways around this, like there's automatic load balancing, where like if you have a machine that you know it's consistently slower, you automatically give it smaller, you know, jobs and stuff like this. I honestly don't know if distributed data parallel considers this, but I don't think it does. There are also ways to do things asynchronously. And asynchronous training is basically a solution to this where instead of waiting and synchronizing all of the things before doing the optimizer step, you might do the optimizer step on each machine, and at certain points, each machine communicates with each other and collects the gradient updates you get from other machines. A very simple example of, or a very famous example of this is something called Hogwild. And basically, this is the simplest possible thing you can do. You send out jobs, and these jobs, whenever they're done, they send back gradient updates, and you update the central gradient repository with these gradient updates. There are reports using this for neural networks that show that this actually works. This works reasonably well. It's what we implemented in DINET for multi-CPU training, for example, and it works quite well. But it becomes more difficult when you have like multiple machines and you don't have a shared memory location for all of the memory, or multiple GPUs or stuff like this. So I think if you're really interested in this, I'm not the world's expert on this. I can point you towards the world's one of the world's experts on this, who's a CMU student. But keep in mind, this is something you can do, and there are different ways to do it. So. In reality, probably for the project in this class, this would be sufficient, and it's what a lot of people use for a lot of different things. Okay, any other questions? Okay. So the next thing I want to talk about is negative sampling. And negative sampling is a way to deal with inefficiency due to very large output spaces. And very often, like let's say we're training a language model, we will want to do computation across very large vocabularies. This would be one example. An even harder example is when we want to do something like retrieval. And I talked about this a little bit before. And in this case, our quote-unquote vocabulary is all the examples in our database. So we want to retrieve the most appropriate example for a particular input. And when we actually do retrieval, we will be searching, like let's say we wanted to do text-to-image retrieval. So we wanted to say, find me the example of a bluebird with a white wing that's smaller than a robin, or something like that. And if we did something like that, all the photos in the world are the potential things that we could be retrieving. So we can't realistically train a model that tries to discriminate between the correct answer and all the images in the world. So there's too many to calculate at every time. So what we do with negative sampling is basically, let's say we have a softmax, like a probability distribution. We have our correct value, and then we have all of our negative samples. And these negative samples are the things we'd like to discriminate from our correct value. So what we do is we subsample all of the parameters here. So we subsample W to be W prime, which has only the correct one in all the negative samples. And we do a similar thing for our bias term, and then we calculate only over this subset. And we can sample these negative samples according to some distribution Q. And this is important if we want to do this in a mathematically good way. So like the softmax, let's assume we have something like this, where we have a score of xi. And the denominator here is what's expensive, because we would have to enumerate over all of our the potential confounding examples here. And so we'll call this zhi, and we would like to approximate this denominator. So kind of a mathematically correct way, or a mathematically like sound way of doing this is something called importance sampling. And basically, if you know about like sampling within the context of machine learning in a machine learning class, you'll know that sampling according to a probability distribution is a good way to basically approximate a big sum like this. So we take a few samples, and if we took enough samples, we would be able to, if we took enough samples, we would be able to approximate this distribution. So let's say we took an infinite number of samples, we would be able to directly approximate this sum down here. However, we don't want to take an infinite number of samples, but we still want to have a good approximation of the distribution. So what importance sampling does is we sample from an arbitrary distribution Q, and then we reweight with e to the s divided by q to approximate the denominator. So what this looks like is basically this. So we take n samples that are sampled according to q, and then we reweight the actual probability distribution here according to this constant. So why is this good? The reason why this is good is because the worst thing that we could do is we could sample a bunch of like completely irrelevant things that have a very small value of this. And that would give us a very bad estimate of what the denominator actually is. So like, let's say we wanted to sample the dog blank. If we sampled a whole bunch of nouns, for example, those are not likely to follow the dog something because we expect to have a verb. So they're all going to have a very small value, which means that we're going to have a very bad estimate of this denominator here. So what we can do instead is we can have a better Q distribution. So let's say this Q distribution was a simple bigram distribution that we calculated beforehand. We don't train this distribution jointly with this model, but it gives us a better estimate of what things are actually likely to have a high value next. And if we sample according to this more accurate distribution, we'll get a more accurate estimate of the final output. To the point where if we sample from this Q distribution, if we sample directly from the correct distribution, we'll get the most efficient approximation of what this denominator would look like. Are there any questions here? Okay. So, however, this could be a biased estimator, especially when n is very small. If n is very small, this will not converge to the true distribution. So this paper on noise contrastive estimation basically went through the derivations and found a way to fix this. And basically the way, I'm not going to go through all the math here because I don't think going through lots of math on slides is the most efficient way to spend time. But the basic idea is we are trying to guess whether whether the sample that we're looking at, whether the word that we're looking at is a true sample or one of n random noise samples. And we want to optimize the probability of guessing correctly. So this, in a way, if people are familiar with adversarial learning, it's kind of like adversarial learning, where you're trying to train something that is discriminating between true outputs and noisy outputs as well. And you can actually demonstrate that this will allow you, with some variance, to calculate the true distribution. So this is a good way to train language models. This contrasts with some simple negative sampling, and this is used in a method called word2vec that I think a lot of people, or a software library called word2vec that I think people are familiar with. And what this does is it samples k negative examples and tries to calculate a very similar objective. But this is unfortunately biased when k is not equal to the size of the vocabulary, or q is not a uniform distribution. So unfortunately, basically negative sampling, if you're sampling anything less than the size of the vocabulary, which is the whole point of calculating negative samples, or this particular method for negative sampling is not a good estimator. So if you actually want to use something like this, to train a language model, you should be using noise contrastive estimation instead. I've been talking a lot about using GPUs, and GPUs are very efficient. And fortunately, GPUs are compatible with negative sampling objectives. And basically, what you can do is you can sample for each mini batch. You can sample the same negative samples for the mini batch. You can do this within the framework of noise contrastive estimation, which I said before is a good way to train models, or is a theoretically correct way to train models. And Zoff et al. 2015, which is in the references, explain how you can do this efficiently. And they demonstrate that they were able to do this to train models with very large vocabularies and nonetheless get very good results. So this is kind of a good way if you want to calculate language models efficiently and not worry about large softmaxes. For things like retrieval, I think it's actually more common to not think about this very carefully and just use like the other examples that you sample in a mini batch as negative examples. There's other things that people do, like they make very large mini batches and try to find hard negative examples to try to fix this. So basically, you take a whole bunch of examples and you subsample down to find only the examples that are very hard for the model to solve. These are heuristics that work pretty well, but something like noise contrastive estimation or importance sampling are kind of like theoretically correct ways to sample the distribution, where things like hard negative mining are kind of heuristic approximations to these. And I have an example of the code here as well. Are there any questions about this stuff? I think this might be a little bit abstract now, but make sure you remember this if you get to the point where you're doing something like a retrieval-based model or doing language modeling with a relatively large vocabulary in the future, because these are things that affect your accuracy and speed quite significantly. Okay. So finally, I'm going to talk about more efficient predictors themselves. So up until now, I was talking about training algorithms. I'm going to talk about ways you can actually change your model to make this sort of prediction more efficient. So a first example is a structure-based, so I'm going to talk about structure-based approximations, like class softmax, hierarchical softmax, binary codes, and embedding prediction. And the class-based softmax, the idea here is that you assign a word to a class, assign each word to a class, and then you predict the class first, then you predict the word given the class. So basically, you predict the probability of a class given the hidden state, and you have a smaller number of classes than your full vocabulary, and then you predict the actual word itself given the class. So the conditional probability of a word that doesn't belong to this class is 0. So you don't even need to worry about it at all. You assume that the word will only get a non-zero probability if it's included in the class, which means that you can just discard all of the words that aren't included in this class. So quick quiz. Let's say your vocabulary size is n. What is the big O complexity of this sort of calculation with respect to the vocabulary size? What is the fastest you could possibly make this? Any ideas? Yes. And so the vocabulary is size n. So the naive way of just calculating the whole softmax, let's say that was n, because you have to calculate each row. Yeah, just the softmax. Yeah. Any other? Yeah.
Is it log n?
Is it log n? A nice try, but no. Yeah.
Square root of n?
Square root of n. Yes, that's correct. And the reason why it's square root of n is because if you think about the optimal number of classes, let's say you have a vocabulary size of 10,000. The optimal number of classes here would be 100, because then your first prediction would be over vocabulary size of 100, and then your second prediction within the class would be if you distributed words evenly across all of the classes. Each class would have 100 words, so you would have you would have 100 classes and then 100 words in each class. So it would be square root of n. So very good. So yeah, sorry, I'll read this. So hierarchical softmax, the idea here is to take this to the extreme. Yeah, sorry.
In the class-based sampling, does it ensure that each word will have just one class, or can that, for example, let's say the word back, it can give both a noun or a word?
Good question. So can you ensure that each word has one class? What about polysemous words? What about words that have different meaning, like two different meanings, or like are both a noun and a verb? You're out of luck if you do that here, basically. So you have to assign each word to a class, otherwise you don't get the computational benefits. I've never seen anybody actually do this, but theoretically you could assign a word to multiple classes if you knew it had different senses. Yeah.
What about gradient passing through the hard decision of the class?
So what about gradient passing through the hard decision of the class? That's not a problem. And the reason why that is not a problem is because you see you're still conditioning on H when you predict X. So you see that the gradient is flowing back into H from the prediction over C. And then the gradient is also flowing back into H from the prediction over X, because you're conditioning on both, basically. So if you were just conditioning on C, then yes, it would be a problem, and you would have no gradient flow back in there. And actually, if that was the case, you could just count and divide to calculate the optimal class predictor, because you wouldn't have any other information to condition it. Good question, though. Any other ones? Okay, sorry.
So this assignment of class is like under the hood, like you don't know which class it is.
So is this assignment into classes under the hood? Like you don't know a priori which class it is?
Right.
And the answer is to get computational benefits, you do need to do it beforehand, before training it all. So the way this is commonly done is through some sort of fast algorithm for learning classes. One very simple example of it would be to train a really fast word embedding model, like Word2Vec, and then do k-means clustering over the classes. That's one example of how you could create classes beforehand. So there's other ways to do it as well. You could do a Glamorous clustering or something like that. But in order to get computational benefits here, you do need to do the assignment to classes beforehand. Yeah, any other questions? Okay. So the hierarchical softmax. So the class-based softmax is a special case of the hierarchical softmax. So what the hierarchical softmax does is it creates a tree structure where we make one decision at every node. So if you look at the example here, our first node in the tree chooses our classes. So you have a branching factor of 100. And then you have 100 nodes, one for each class, where you make another choice over 100 words each. So that would be the example for the class-based softmax. But of course, you can make other tree structures. So one example would be a binary branching tree. So a binary branching tree looks like this. So you, in your first choice, you go up. You choose up. In your second choice, you choose down. Your third choice, you choose down. Your fourth choice, you choose down, up. And then you get a word. And if you convert this into binary, this shows that your word was number 14. Because you went up, which corresponds to 0, down, which corresponds to 1, down, down, up. So you have 0, 1, 1, 1, 0. And you can just read this off and say, now I'm at word number 14. So what is the computational complexity of this? And okay, there we go. Yeah. So log 2. So I thought I would give you the chance to answer first. So this is log 2 because you basically have a binary decision for each one. So if your vocabulary is size n, you need n bits to express the word ID. So if you went even further, you can go to directly predicting all of these bits. Oh, so one problem with this is if all of these decisions kind of depend on each other, this can become complicated. So like, let's say if your prediction up here was different than your prediction down here, depending on the binary value of the word, you would have to use different parameters in each of these predictions. So what there's also a method of binary code prediction, where basically what this does is instead of, the original paper was not by me because I was not old enough to be doing research yet, unfortunately, but the second paper is by a former student of mine, so I should mention that, so you can take it with a grain of salt when I introduce this paper. But basically the idea is you multiply by a matrix and you take a sigmoid, and this sigmoid gives you binary decisions, and then you can just use this as your word ID when you read it out. So instead of calculating a softmax over n words, you can calculate sigmoids independently over each of log n outputs and actually make predictions. This is very simple and fast to implement on a GPU. Can anybody think of a problem with this? Any ideas? Yeah.
One error might change significantly the word, while
right.
Maybe in the softmax it would be something that still is quite likely.
Right. So one error might change the word significantly, or one error changes the word completely from like dog into lettuce, or something something else completely unrelated, right? So there are some improvements to fixing this. So we tried a hybrid model that predicts these binary codes only for rare words, which is where you get the big gains anyway, right? You have softmax over the top, n words, but then you have the sigmoid over the rare words. And we also use something called error correcting codes, where you basically expand the number of binary values so that even a small mistake or two will not cause you to mess up your outputs. So I think this is an interesting paper if you want to take a look at it. And we have a code example. And then finally, there's a paper by Sachin Kumar and Yulia Svetkov here at CMU, which I also think is very interesting. And what they did instead is, it's similar in that you're still predicting a fixed size vector compared to like we talked about in the binary codes. But what you're doing instead is you're predicting a vector, and then you're taking its nearest neighbors with respect to word embeddings that you pre-trained according to something like word2vec or something else. And then the distance in this embedding space becomes your loss. So this is good because now you don't need. This is independent of your vocabulary size. This is you can see that it's dependent on your embedding size, but as long as you can learn good embeddings with a dimension of 512, it doesn't matter how big your vocabulary is. You're still only going to be predicting 512 values. So this is O of 1 in your vocabulary size in terms of training speed. There's a few things to mention here. Number one, they had to use a special loss function called the von Mises-Fisher loss, or loss according to the von Mises-Fisher distribution. And the basic idea here is that this is making the embeddings close on a unit ball. So it's not exactly the same, but kind of intuitively, you can think of it as maximizing the cosine similarity between the embeddings. And the good thing about this is this, basically, the cosine similarity has this normalization so that the length becomes 1 with respect to all of the outputs. And that makes basically the learning problem sufficiently hard that that it becomes a good training signal for training sequence models, for example. There's a couple other problems with this, or not problems, but things that could potentially be interesting to think about. Still at decoding time, when you're generating outputs like in a sequence model, you still need to calculate over the whole vocabulary. So how can you avoid doing that? Another thing is, what was I going to say? The embeddings are pre-trained, usually. So if the embeddings are pre-trained, how could you fine-tune the embeddings jointly with a learning procedure like this? So I think this is a very interesting method, and there's lots of additional things to think about. OK, so that's all I have for today. Are there any questions before we finish up? Yes.
In the last slide, you said the sequence of the one. But if you have to calculate the distance with the nearest embedding, isn't that order that you would be making a comparison with the other?
OK, so the question is, if you have to calculate the distance with the nearest embedding, wouldn't you have to find the nearest embedding anyway, which is expensive? That's basically the question.
Yeah, I mean, how is this order?
So the distance isn't with the nearest embedding, it's with the embedding for the gold standard answer. So because of that, you already can just look that up. Yeah, good question. Any other questions? Yeah. Yeah, so even if the vector is not on the unit ball as a result of calculating either of these two vectors, it gets renormalized to the unit ball, essentially, and you find the distance on So in a high dimensional space, the unit ball basically, it becomes harder to find things that are close on the unit ball, right? Like there's kind of a funny analogy about high dimensional spaces where if you have a cream puff that has like lots of delicious cream in the middle, if you write it in 2 dimensions, you don't have very much crust. But if you put it into 1,000 dimensions, the amount of crust becomes like 999 1,000ths of the cream puff. So you don't want to be eating a high dimensional cream puff. But but basically yes, it becomes a lot harder to find close things on the unit ball in high dimensional space. But I think that actually makes training this model easier because you're making the learning problem harder. So in order to do that learning problem well, it has to do a good job of matching the vectors. So that's a good question. Yeah.
Is there time to go through the example you were going to go through in the beginning of the class? You said if this time we'll go through an example.
Oh, yes, yes. The example at the beginning of the class. Sorry, what did I say I was going to go through again?
It was about, I think it was a bad case, like make it more efficient. You open something on GitHub.
Oh, the example, I think in the interest of time, I'm not going to go through the example, but if you want to go through it yourself and ask any questions, I'll be happy to do that. Okay, anything else? Okay, I'll finish up.